Hello and welcome to the fourth lecture of our this current module, module 3. This module is on random variable, and in this lecture we will cover that further descriptors of random variable. Basically, in the last class what we did, we started with the description of the CDF, and after that we started some of the descriptors of the random variable. If the in absence of the proper definition of this PDF and CDF, if we know some sample data, then from the sample data we can define some descriptors of the random variable, and with that we get some idea about how the particular random variable PDF distribution, the behavior of the PDF we know. So, in the last class we saw that its central tendency, and that central tendency, as we saw that it is in terms of its mean, mode or median, and then we saw that coefficient of dispersion, that is measure of dispersion in terms of variance and standard deviation. So, today's lecture that we will start, we will start with some more further descriptors of this random variable, and we will start with skewness and kurtosis. The skewness and kurtosis are the higher moments, as we are just describing in the last analogy that we have given that analogy with this moment. So, these are the higher moments with respect to the mean and standard deviation. So, we will see that one first, that skewness and kurtosis. Then we will see some analogy with the moment of area that we indicated in this last class, and with this we will start that moment generating function and characteristics function. These two are very useful function, and if we can define these functions, then we will see that the description of all such moments, that is basically this mean, standard deviation or mean, variance, skewness, kurtosis, this is up to 4th, and above also that higher moments are also possible. So, we will see that how if we know the moment generating function and characteristic function, then how all these moments, any order moment of any order, how it can be defined with help of these two functions. Then we will start, because these are for this for some distribution, for if some sample data is available, then how we can that particular sample data we can represent graphically, so that we can have some idea about these descriptors with respect to its graphical representation. So, this is we will try to cover today's lecture, and we will start with the skewness. As we told that the skewness of a random variable is the asymmetry of its probability distribution. So, this is a measure of the measure of skewness may be expressed in terms of this expectation of x minus mu x. If you recall that in the last class what we discussed, that the first moment when we are when we are looking for the central tendency, we take the moment with respect to the origin, and so it gives that the distance from the origin to that PDF, which is nothing but that its mean, the location of its mean, that we will show in a minute in terms of some graphical representation. And now all the higher order moments, if we take it with respect to the mean, if we take, and in the last class we concluded that the first moment with respect to the mean is becoming 0. So, this skewness that what we are talking about, this is also a moment with respect to this mean, and that mean it is the third moment, and second moment we discussed in this last lecture, that it was the variance. So, this is a measure of symmetry about this mean. So, how this particular distribution, if we see it here, then we will come to know that. Now, from the origin I know how it is distributed and all, so we know that where it is the location of this mean. Now, what we are trying to do from with respect to this symmetry, that with respect to this mean whether it is symmetric or not. So, if it is not symmetric, then how it is distributed about the mean, that is the goal. So, that is why when we are taking the third moment, that is x minus this mu, so this sign remains. Sign remains means it will show that if it is more this side, then it will be negative, and if it is more this side it will be positive, means more means that more disperse. If the dispersion is more this side, then it will be this will be negative, and if it is this side, then it will be positive. So what we will do, we will just take the expectation of this one as usual for in case of this discrete random variable and in case of this in case of continuous random variable. For this discrete, the expectation we know that now this is becoming, if you see, this is becoming a function of this random variable. So x is our random variable, and this x minus mu x power cube is a function of our random variable x. So we know how to take the moment, we know how to take this functions as the expectation of a function that we described in the last lecture with respect to the gx. So this function will come, will be multiplied by that probability density, or for the discrete it is the probability value for that particular outcome, and we will sum up all these things to get the what is the moment with respect, what is the third moment with respect to the mean. And similarly for the continuous random variable x, where its PDF, if its PDF is defined by this fxx, then this expectation of this function again will be expressed in terms of a, so this summation now is converted to this integration, and this integration over this entire support of this random variable x, we have taken it from minus infinity to plus infinity. So this gives that cube multiplied by the density, and if we do this integration, we will get the measure of skewness. So this will get the third moment of that variable with respect to mean. Now if we now see that if the probability distribution is symmetric about this mean, then its this moment will be equal to 0. This will be 0 because whatever, now if you see here, now if I draw one particular distribution which is symmetric, now this is your location of mean. Now what we are doing, actually we are taking a small area, and as this is that distance, as what we are taking x minus mu x, and this power is cube, so that whether this is on the negative side with respect to this mean, or this is, so this is on the positive side with respect to this mean. Now being it symmetric with respect to this one, being this power 3, these two are cancels out. So if this one is symmetric, then this moment will be exactly equals to 0. So this is what is explained here. If the probability distribution is symmetric about mu x, then this expectation of x minus mu x power cube, this is third moment, is equals to 0, which is one example is also shown in this in this diagram. Now we will compare with this symmetric, this black one again we just written, which is we know that this is symmetric, for which this third moment with respect to mean is 0. Now if we see this blue one, this blue one is known as the positively skewed. Now we will see how this one is positively skewed, how it is distributed. Now if for x greater than mu x, the values are more widely dispersed than for the x less than equals to mu x, then this will obviously become positive. So if this is becoming positive, then this skewness, the skewness of this blue PDF is positively skewed. We say it is positively skewed. Now this one is greater than for this zone. Now if I just draw another one here, what is meant by this one is, now as this side is dispersed, if we take this mean, maybe the mean will be somewhere at this location, this mean will come here. Now if we see the data range from towards the negative side, towards the left side of this mean and the right side of this mean, that is, this is your mu x. So this side, if I say this is your x is greater than mu x, now, and this side is your x less than mu x. Now you can see that this side, when widely spread, when this is widely spread, then compared to this one, this is lesser, this is more dense compared to the right hand side. Then when we are taking that x minus mu x power cube, this is giving you more weightage. That's why the total summation will be positive in case when it is skewed like this. So that example is shown here. So somewhere the mean location will be in this here, where the right side, the positive side with respect to the mean, will be more dispersed than compared to this left hand side. So that resulting in that, so this side it is more, so this quantity will become positive. So this blue PDF what is shown here, that is positively skewed. Just opposite, if we see, we will get that what is called the negatively skewed. So in this case it is just opposite, that is x less than equals to mu x. In this zone, in this region, the values are more widely dispersed than for that x greater than mu x. So somewhere in this location, in this point, this that mean will come, and this side it will be less dispersed compared to this side. So obviously due to this power cube, this quantity will become negative. So what is shown here by this blue line, this PDF is known as a negatively skewed PDF. Now for up to this second moment, what we have seen that it can be viewed as a power of this random variable when we are taking this moment with respect to the mean and we are taking it as a square, then obviously that particular quantity is also having the same unit that the random variable is having. Now for our convenience, when we are increasing the order of this moment, when we are going for this third moment or fourth moment, then keeping the same unit may not be that convenient. So to make it convenient, what we do is that value, that moment is generally normalized with respect to its some power of the standard deviation. So the power of the standard deviation is selected in such a way that the quantity becomes dimensionless. So this is exactly is done here to get that, and which is known as this coefficient of skewness. So the coefficient of skewness here is the convenient dimensionless measure of asymmetry given by. So this is your expectation of this this function, which is the third order moment. Now this is obviously this quantity is having an unit of this cube of the unit of this random variable. So the standard deviation also we are taking the same power to get the coefficient of skewness. So the coefficient of skewness, as we are dividing it by this power 3, this is becoming the total quantity, this gamma becoming dimensionless. So this now if this becomes 0 in case of the perfectly symmetric PDF, perfectly symmetric probability density function, then this, when it is becoming 0, this function is becoming, this value becoming 0. So the gamma equals to 0 indicates that this is a symmetric PDF, and if it is positive, then it is positively skewed, if it is negative, then it is negatively skewed. So this denominator is only to make this quantity dimensionless. Now this is from the now if we have some sample data, if we want to calculate this ones, calculate this measure, that is this coefficient of skewness from the sample data, there are some sample statistics based on which you can calculate this coefficient of skewness. Now this coefficient of skewness, the sample estimate of this coefficient of skewness is expressed as this, where we take the individual observation and deduct it from the mean. So it is giving basically the distance of each and every observation from the mean, and we are taking its power cube, summing it up for the all observation. This n is the number of observation as shown it here, n equals to number of observation. So we are summing it up, multiplying it by n, we will come to this one, and divided by this is the sample estimate, this s is the sample estimate of the standard deviation that we discussed in the last lecture. So this is the sample estimate of the standard deviation, we are taking its power cube, So this unit and this unit get cancelled, and these are the normalizing constants. So this n divided by n minus 1 multiplied by n by 2, just to make this one is consistent and unbiased. So this is this total quantity. What is given is that this is your the coefficient of skewness depending on this data available from x1 to xn. Now we will go to this fourth moment with respect to the mean, and which is known as the kurtosis. Now, so the measure of kurtosis is the fourth moment with respect to mean. So we are taking the expectation of the function x minus mu x power 4. So and again, to make this one dimensionless, what we are using is we are using that this sigma x power 4. Now as this again similar to this coefficient of skewness, that is we are taking the power of this standard deviation 4 to make this total unit total this one as the unitless. Now what is important here, what does this coefficient of kurtosis implies? For example, thus we have seen that mean, what does it mean implies, because this is a central tendency, that then the coefficient of variation, it is the this is indicating that its dispersion with respect to mean. Then skewness is showing how whether it is more spread towards the right hand side of the mean or the left hand side of the mean. So that is a measure of symmetry. Now what is this kurtosis? If we see, then we will see that this is also power 4. So as it is power 4, and obviously for the whatever on the left hand side and the right hand side, that will be negated, and that will make 0. Now this 4 is actually a measure of peakedness. Now this measure of peakedness means how the peak, how does that particular peak of this PDF look like. Now if we see here, if you see that, if you can see the difference between, say this is 1, so this is also a symmetric distribution, and if I draw another one, this is also another symmetric distribution, and their mean are also say same, their mean are also same. So the first moment is same, second moment is the variance also will be same. If we just see the total thing, so we will see that the variance of these two distribution with respect to the mean will be same. Now the coefficient of the skewness also will be same. In the both the cases it is symmetric, so that's why it is both the cases will be 0. Now the difference of this peak of this, how it is peak at this point, that will be reflected with respect to its fourth moment, and that's why this fourth moment, when it is normalized by the fourth power of the standard deviation, which is known as this coefficient of kurtosis, this is known as this measure of peakedness. Okay. So this measure of peakedness with this one having a sample statistics of this kurtosis, again the sample estimate of this coefficient of kurtosis is expressed in terms of this, that is each and every individual is measured the distance from this mean power 4, summing up for this all the observations, and divided it by the fourth power of the standard deviation and this normalizing constant to make this estimate unbiased and consistent. Now this one will be equal to 3 in case of this mostly used distribution known as this Gaussian distribution or normal distribution. So for this normal distribution, if we calculate this quantity, so this measure of peakedness will become equal to 3. Now if I say that this measure of peakedness is less than 3, then we will say that this peak is little bit lesser than this standard normal distribution, and for that and if it is more, if the peak is more, if it is more than 3, then it is more peaked than with respect to in compared to that normal distribution. So this one, sometimes in some of the text this sample estimate is also expressed in terms of this -3, just to make that this k, if the k is equals to 0, then it is for the same to this normal distribution, and if it is negative then it is lower than normal distribution, if it is positive higher than normal distribution. But this is also correct. So we have to take that this is equals to 3 in case of this normal distribution. So with this, what is there afterwards, you can now understand that we have discussed about this first moment, second moment, third moment, fourth moment, and obviously the first moment with respect to the origin we discussed. Then we have seen that first moment with respect to the mean is 0, second moment with respect to the mean, and we understood what is its implication. Then third moment with respect to mean, fourth moment with respect to mean, and in this way we can go on increasing. We can go for the fifth, sixth and seventh moment, and for each cases you will get some of these descriptors, and up to this fourth one it is almost describing almost everything. But still we will say, if we can get that if we get the measure of this all these kinds of kinds of coefficient, that is all these moments with respect to mean, if we say, then we can equivalently we can say that all the properties of this of the PDF is known to us. But so in that one we will just see in a minute that how this one is related, how we can say that from a single function how we can get all these measures, all these moments, that we will see. But before that, these moments, this analogy of this, why this is called moment, that is its analogy with respect to the area of the PDF will be discussed now. So now see, if we say that this is one of the standard PDF that we have shown here. Now its mean will be some point where its CG is. Now considering a unit area having the general shape as shown in this following figure. Now this is, if I take a very small area, very small length along this x-axis, which is dx, and if we calculate what is the total moment, and this is your origin. So if we calculate what is the moment that is due to this particular area, then this distance will be multiplied by this total area to get this one. Now if we integrate this one, this full area, then we will get what is the total moment of this area with respect to the origin. Now if we divide that quantity with respect to this total area, then we will get one distance, that distance from this origin, that is passing through its CG. So this is this. So and we know that from this properties of this standard properties of this PDF, that this area, total area, is equals to 1. Now if we just see this discussion here, is that the centroidal distance x0 of this area, that is x0 is equals to, so this one what we are doing is that particular area, that is fx multiplied by dx. So what is this? So this one, this height here, which is that fx at the location x, that multiplied by this small infinitesimal small length dx, that is giving this area. That one multiplied by this x is giving you this moment, and if we integrate from minus infinity to plus infinity, we are getting the total moment, and that divided by area obviously is giving the distance of this centroid of this particular area. And we know that this total area is 1. So this one is equals to x, the centroidal distance from this from the origin, is equals to integration minus infinity plus infinity x multiplied by fx dx. Now what is this again? This is nothing but the expectation of the x. The way we define that expectation of the x is that x multiplied by fx dx. So this distance is the centroidal distance of this area from the origin is nothing but its mean. The distance from the origin to this one is nothing but its mean. So it is, so as this one is also the moment with about origin of this irregularly shaped area, just comparing this with the expression for the mean or the expected value of a continuous random variable, the mean can be referred as the first moment about the origin of the PDF with respect to the random variable. So this is how we just drawing the analogy between this total area taken its with respect to this moment and multiplied by its distance from the origin. So this first moment about the origin is nothing but is its mean, which is equals to this function is nothing but equals to its expectation. Now, if we want to take the second moment with respect to the origin, then this area multiplied by this distance square will give you, divided by total area will give you the sorry. So, this area multiplied by this distance square will give you that second moment. Now, this second moment, the what we have seen is that with respect to instead of taking with respect to the origin, for our convenience we take the second moment onwards, we take that with respect to this location of this mean. So, this x naught, in case of this first moment, this x naught what we have shown that as a distance from the origin to the centroid of this area is nothing but from this expression, which is reflecting that this is nothing but your this is nothing but the expectation of this x, which is nothing but this mean. So, this point is the distance from this origin to this mean. Now, the second moment, now what I told, I repeat that from this second moment onwards we calculate it with respect to this mean, and we take this distance from this mean to this infinitesimal small area and multiplied by its distance and calculate its moments. So, the moment of inertia about the mean, that I was telling, there is the second there is a moment of inertia, second moment, that is x minus mu x. So, this x minus mu x is coming from that, as because we are taking it with respect to the mean. So, that distance, now this function which we are taking first only x, because that was from the origin, that was actually that was x minus 0. So, as we are taking it with respect to the mean, we are taking that x minus mu x, and second moment, so we are taking its square multiplied by this small length dx and its value at that point x, and this quantity we are integrating it for this full support area to get this one. So, this is also what we see is that this is also now this one from this earlier expression of these moments, this is the second moment about the mean of this irregularly shaped area. So, comparing it with the expression for the variance of a continuous random variable, the variance can be referred as the second moment of the PDF of a random variable about the mean, what we discussed so far. And also in the last class we at the towards the end we discussed the first moment with respect first moment of the PDF of a random variable about the mean is 0, and this is discussed why it will be 0, because whatever the right hand side of this mean and left hand side of this mean and power obviously will be 0, will negate each other, will cancel each other. That is why that moment will always become 0 irrespective of the shape of the PDF. So, in general, if I see that nth moment of a random variable about the origin is expressed as expectation of x power n. If I just now we are taking it with respect to the origin, that is why x power n is minus infinity to plus infinity x power n f x dx, and the similarly that nth moment of the random variable about mean is expressed as that expectation x minus mu x power n is equals to minus infinity to plus infinity from this x minus. So, this expression that we have seen, that this is for the nth moment with respect to the mean. So, hence the coefficient of skewness can be referred as the third moment of the PDF of a random variable about the mean normalized by its cube of the standard deviation. This is exactly what we discuss when we are discussing its estimates. So, this is the cube of the standard deviation, means this we are taking the third moment to cancel this one, to make it dimensionless, we are normalizing it by with respect to the cube of the standard deviation. Similarly, for this coefficient of kurtosis, this can be referred as the fourth moment of the PDF of a random variable about the mean normalized by its fourth power of the standard deviation. So, this analysis if we keep in mind, then we know that why we call this quantities as the moment of that moment of the PDF with respect to origin or with respect to mean, as the case may be. Now, as just few minutes back I was discussing that these 4 things that we have discussed, that is central tendency, variance, variation, dispersion, then then its measure of symmetry, measure of peakedness, all these things are the representation of one moment with respect to one moment with respect to that with respect to mean, and in this way we can go on increasing to take the moments from the fifth, sixth, seventh, and in this way. So every time I have to define that function, I have to normalize this to this one. Now the next thing that we are going to discuss is the moment generating function, and we will see with the help of a single function how all the moments can be known. And this is very important in the sense, if all the moments are known, then it is equivalent to know all the properties of this PDF. That is why this moment generating function is very important, and this is what we are going to discuss next. So this moment generating function, the expectation of e power sx, this x is the random variable here. So this e power sx is again a function of the random variable x. So expectation of e power x sx, which is a function of the random variable x, is known as the moment generating function of that random variable x. So I have to take the expectation of this value. So how this expectation looks like? So this moment generating function, which is denoted by gxs, is expressed as gxs equals to expectation of e power sx equals to minus infinity to plus infinity, e power sx, this function I am taking, and that multiplied by this probability density function, and integrating with respect to dx minus infinity to infinity. So this is this function, this particular function is your that moment generating function. So if x is discrete, then this is for this continuous, that's why we took this integration. Now if x is discrete, then again so gx is expressed as the similar way to how we express that expectation of a function of random variable, of a function of a discrete random variable. This is the summation of all xi e power sxi multiplied by the value of this probability all those respective points. So this is your, so this is this expression for the discrete random variable, and this is for this continuous random variable, is nothing but this moment generating function. Now we will see why these things are how these things are useful and why these things are important. Now this usefulness of this moment generating function, that first derivative of that gxs evaluated as x equals to 0 results in the expected value, which is the first moment of the random variable with respect to the origin. Now derivative of this gxs, and so this is the first derivative I am taking, and after this derivative I am putting that x equals to 0. So by this simple calculus we will get that from this will basically turn to that minus infinity to plus infinity 1x we will get due to the derivative, and e power sx, when we are putting s equals to 0, that becoming 1. So that is 1 multiplied by fxx dx. Now this function is nothing but the first moment of that of the PDF. So when we are taking this derivative, when we are taking the first derivative, the resulting function is your first moment with respect to the origin. Similarly, the second derivative of gxx evaluated at x equals to 0 results in the second moment of the random variable with respect to the origin. Let us see. So we are taking this derivative, the double derivative, and evaluated with respect to ex. So this x now is becoming x multiplied by x, that is x square, multiplied by e power sx, s equals to 0. So e power sx equals to 1 multiplied by this fxx. So this is nothing but again that second moment with respect to, this is the expression for the second moment with respect to origin. So thus if we just continue the first moment, second moment, and in general if we want to express that the nth derivative of gsx evaluated as x equals to 0 results in the nth moment of the random variable with respect to origin. So, this that nth derivative here again. So, this as we are taking this nth derivative, this x power is becoming n, and which is nothing but the expression for the nth moment of the random variable, basically the PDF of the random variable here. So, so this is this is how we can use this one. So, if we know this gxx, now we can take the derivative of whatever the derivative that we need. So, whatever order of this derivative that we need, that the nth order. So, this n can be in general. So, nth order derivative we can take, and we put that x equals to 0. So, we will get directly that nth moment. So, this is the usefulness of this moment generating function. Now, there is another one called the characteristics function. This expectation of this e power I s x. Now, instead of putting that s x, we are putting one complex variable, that is I is equals to square root of -1. So, if we take the expectation of this one, this expectation is known as the characteristic function of that random variable x. So, and it is denoted as, this characteristic function is denoted as phi x s. So, we know if it is the expectation of this one, so this can be expressed as that expectation of this e power I s x, which is the integration of this -infinity to +infinity e power I s x f x x dx. Now, how we can relate this particular function with respect to the moments, that, so we can take that again for this characteristics function also, we can take that nth derivative of that one, and we can multiply it by 1 by I power n, and that function is evaluated at s equals to 0, which is nothing but will give you that expectation of x power n, that is the -infinity to +infinity x power n multiplied by f x x dx, where I equals to 1. This characteristics function, use of this characteristic function is mostly seen in the electrical engineering, not much in the civil engineering, but this moment generating function is important, important in this field. Now, as we have seen that we have some descriptors of this random variable, and that random variable we have discussed, and from this, now if we have some sample data that is available to us, now that sample data we have to first of all represent graphically, just to see how its shape look like, how it is displayed, so that how it is displayed, so that we can get some idea about its distribution pattern, about its distribution. So, now this graphical representation of this sample data meant for any random experiment, that outcome, that data that we are having in the context of this civil engineering, we can take that stream flow data, rainfall data, or the strength of the concrete, number of accidents on the particular stretch of highway. So, these are some sample data that we can see, and now if we want to see that how this random variable behaves, so we have to plot that data first, and we have to see that how this distribution look like, and there are few techniques how graphically we can represent that particular data set. So, that is what we are going to discuss next, to different ways, different popular ways how we can represent the sample data in terms of the graphical views. Okay, before that we will just to conclude that the descriptor of the random variable, we will put some note on this, that the description of the probabilistic characteristics of a random variable can be given in terms of this main descriptors of this random variable. The central value of a random variable can be expressed in terms of mean, mode, or median, that we seen in the last class mostly. That mean is also called the first moment of this PDF of the random variable about the origin, that we have seen when we are discussing that representation of this area, that is analogy with this moment of the area of PDF. Then the dispersion, asymmetry, and peakedness of the PDF of a random variable are described in terms of their second moment, third moment and fourth moment of the PDF of the random variable about its mean. This is important. So that when we are taking this, when we want to know that is dispersion, asymmetry and peakedness, we are taking that moment with respect to its mean. And last we saw that this moment generating function and this characteristic function are helpful because this helps to obtain all the moments of a random variable in an alternative way. Now, just now we are discussing that, we will now see what are the different techniques that this sample data and this sample data how we can represent in terms in graphically we can represent that sample data. So, for convenient representation of data, a data set may be divided into halves or quarters. When an ordered data set is divided into halves, the division point is called the median. So, ordered data set here means that we are just arranging the data set in an increasing order, and we see that where it is exactly dividing it between two, and that division point, that particular point is known as the median. As we have seen that it is a 50%, when the 50% probability is covered, then we call it this median. So, and when an ordered data set is divided into quarters, that is 4 different quarters, then the division points are called the sample quartiles. So, these are some terms that we will know in detail. That is, first is that our quartile. So, this first quartile is the Q1, represented as Q1. It is the value of the data set such that 1/4 of the observation are less than this particular value. So, so this is the first fourth. So, when we are taking this a data set and we are just making it in an increasing order, so it is that particular point when we say that 1/4 of the observation is less than that particular value, that is the first quartile. Similarly, the second quartile means when we are talking about the 50% of the data, that is half of the data, that is it is a value of the data set such that the half of the observations are less than this particular value. So, this is known as this quartile, which is also equivalent to the median, just what we discussed, because it is the half of the data is less than that particular value. And the third quartile is similar to the earlier, but this is that 3/4, that is the 75% of the data when it is less than. So, it is a value of the data set such that 3/4 of the observations are less than this particular value. Now, why these things is important, this quartile are important, so that if we know that the different quartile, if we know the total range of this data set, and after that if we know that what are its quartile, then this will give you some idea that how the distribution of the data set over a particular range, whether if you see that there are a lot of data is there within the first quartile or within the below the first quartile or in between the first and the second quartile or whatever it is. So, this quartile, when we are giving this quartile value along with the total range of this data set, this helps us to understand how dispersed the data set is over its entire range. Otherwise, the simply if we see that what is this median value, that gives only that where the 50% data is there. So, instead of that, if we get a distributed fashion like this, then it will be helpful to know its dispersion, and it will be more graphically it is done in terms of the different box plot that will come in a minute. Before that, we will see that in terms of the percentile. So, when we talk about the percentile of a particular data set that is available to us, that a 100 multiplied by pth percentile. So, before I go this one, this p is your cumulative probability. So, here p, so if we see that p is the cumulative probability, so that it varies from the 0 to 1. Now, for any percentile value, if we, so for the p equals to 0.1 means this quantity will give you the 10th percentile, or p equals to 0.6 will give you the 60th percentile value. So in general, the 100th percentile value in an ordered data set means you have just ordered data set means it is arranged in an ascending ordered data set in such that the 100 multiplied by p% of the observations are equal to or less than this particular value. So basically from the quartile to the percentile, so percentile we are making it more general and defined for each and every value that we need. So by making this p is any number is any continuous number from starting from this 0 to 1, put in any value, that particular percentile will be obtained. Now if we just want to see that quartile with respect to the percentile, then it is very easy to compare that this first, second and the third quartile are equal to the 25th or 50th and 75th percentile values in an ordered data set respectively. So this first quartile is nothing but the 25th percentile, second quartile is nothing but that 50th percentile, and third quartile is nothing but the 75th percentile. Now in this kind of representation, if we want to present in a graphical way, then we will see that this can be done through a box plot. Now to prepare that box plot, we have to know we have to know the percentiles, particularly for those at quartiles, that is 25th, 50th and 75th, and sometimes the 5th and 95th as well. So to get a particular percentile, that is 100th percentile, how can we calculate that percentile? So these are the steps involved in that. So suppose that there are total data set, number of data set that is available is n. So n observations of the data set are ordered from the smallest to the largest, that is in an ascending order. The available data set of size n is arranged first. The product of n p is determined. So if p is known, a particular desired percentile is known, so that particular p value is known to you. So I know this total number of data set available n. So n p, this product, that multiplication of n and p is known. Now if this n p is an integer, so n p can become one integer or it can be, and it may not be an integer. So if it is an integer, say that integer is k, then the mean of the kth and k plus first observation. So from kth and immediate next observation, these two observations are taken and their mean is calculated, and that gives that 100th percentile. If np is not an integer, then it is rounded up to the next highest integer, and the corresponding observation gives that 100th percentile. This can also be done with respect to that you can also linearly change this particular with respect to, if it is not an integer, then these two values, that is a kth and in between this k plus first observation, in between these two, this also can be linearly can also be linearly interpolated, or for simplicity's sake it can be taken to the nearest integer value, and that particular value will give that 100th percentile. Well, so now in this way, whatever the desired percentile is required, that is known to us, and we can represent that information in terms of the box plot. So the information regarding the quartile and the interquartile range in an ordered data set can be depicted with the help of a diagram called the box plot. Now the significant information depicted on a box plot are the sample minimum, first quartile, median or second quartile, third quartile, and sample maximum. So these 5 points are essential before we prepare one box plot. So we know that how to get that from a data set. Just now we have seen how to obtain this first quartile, how to obtain the second quartile and third quartile, as well as a sample minimum value and as well as this sample maximum values. Now once we get this information, this is represented in such a way that range between the first and the third quartile, first means that 25th percentile and third is the 75th percentile, the range between these two quartile is represented by a rectangle. So, and the median, so if I just one after another, if I just draw it here, so this one is your that first quartile, and this one say is your third quartile, and this is represented in terms of a rectangle. Now the second step is that the median value is represented by a line within this rectangle. Now this median value with this one is that it can be either it is not necessarily that it will be exactly middle of this rectangle, it can be any point either this side or towards that side it will be. Then the range between the first quartile and the minimum value and also between the third quartile and the maximum value are connected by lines. So that the minimum, suppose that this is the minimum value and this is the maximum value, then these two are connected by the lines. So these two are connected by these lines. Now again, for the very large data set, that 5th percentile and the 95th percentile values may be used in the place of the sample minimum and the sample maximum respectively. So here is one representation is shown. The dispersion and the skewness of the data set, as we just discussed, is can be indicated by the spacing between the parts of the box in a box plot. The box plot can indicate the outliers, if any, in the population. So here is one example is given. So this is the real axis and where this box plot is shown. So this is the 11.1 is the sample minimum or the 5th percentile, 19.85 is your first quartile, 23.9 is the median or second quartile, 27.85 is the third quartile, and 36.7 is the 95th quartile or the sample maximum value. There are other ways also how we can graphically represent this one. The first one is the histogram. In a histogram, the area of the rectangle gives the probability, and thus the height of the rectangle is proportional to the probability. The rectangles representing the successive values of the random variable always touch those adjacent to them, so that there are no gaps in between. So here is one example of this histogram is shown, so that any height of this rectangle is proportional to its probability. Basically, in this range, number of that frequency in this particular class is shown by these numbers in this axis. So obviously the height of these rectangles are represented by this histogram. Now how we can be useful to this one? By graphically looking this one, we can see about its distribution, how it looks like, and we can fit some our desired distribution like this. We can have some idea how the distribution looks like. But there is another one called the probability bar chart. So in a probability bar chart, the height of the rectangle is equal to the probability. However, unlike the probability histogram, the width of this rectangle has no meaning, no significance. The rectangles representing the successive values of the random variables do not touch their adjacent one. So obviously that there is no meaning, only the height of these bars are important, and which is showing your probability. So here is one comparison. When we call that probability bar chart, that means this at this particular data point, this is the probability associated with this one is 2. This can also be scaled, so that this height of this rectangle that time we will say that it is proportional to the probability. So these are the how we can represent. So this is the histogram, how you can represent the sample data, just to get the idea how it is distributed over the entire range of this sample data. So with this we will stop today, and next class we will see some description of this discrete random variable. So today what we learn is that some more descriptors of this random variable and their analogy with this moment of area represented by this PDF, and then we have seen that how the graphically we can represent the sample data to get the idea of their distribution over the entire range of this sample data. So we will see next lecture with the description of this discrete probability distribution. Thank you.